how does one find the intensity generally as a function of theta, the diffraction pattern, generally as a function of theta for a single slit? Well, we need to establish a way to add all the dE's up. We don't just add E1, E2, E3. We have to integrate over dE. And how does one do that? Well, the magic method, once again, is phasor. Okay, is phasor. Except this time, instead of 2 phasors, 1 from each slit, I'm going to have many phasors. As a matter of fact, I would have infinite number of phasors. Okay, here is phasor 1, 2, 3, 4, 5, and so on. They're infinite numbers. Now, each phasor represents a tiny electric field coming from one tiny part of the source, and therefore it is very short. Okay, because the magnitude is very small. So here is delta E1. That is the phasor coming from this tiny part near the top of the screen, near the top of the opening, and then delta E2 represents the phasor coming from the next part of the opening, and then delta E3 and E4 and so on. Okay, now suppose I divide this divide this opening evenly. Okay, then it is clear that delta E1, delta E2, delta E3, these should have the same phase difference relative to one another, right? In other words, you start with delta E1, and as you turn to delta E2, you go through a tiny phase difference, and you turn from delta E2 to delta E3, you go through the same tiny phase difference. Okay, and then going from delta E3 to delta E4, you once again go through the same tiny difference. In other words, you start with this phasor, you go to the next phasor, go to the next phasor, next phasor. Every time you have to turn the same small angle. Okay, so the phasor is turned uniformly like this. Plus, the length is extremely small. So imagine you have a whole bunch of tiny phasors, each extremely short, and as you add them together, they turn around at an even pace. What do you think you'll be getting? What do you think you'll be getting? You'll actually be getting something like this. Isn't that right? And since the angle is turned uniformly, what do you think the shape of this curve would be? It would be part of a circle, wouldn't it? Okay, part of a circle. Let's say here is the first phasor, here's the last phasor. Okay, then what is the resultant phasor? Well, the resultant phasor is just going, the phasor going, the vector going from the first to the last, like this. This is the resultant phasor. Okay, so we are now going to learn how we can obtain this resultant phasor from this arc, which is part of a circle. Okay, this again is really the summation of a whole bunch of tiny phasors. Okay, so let's learn how to do that. What I have here is a diagram. This red curve here is part of a circle. It represents the addition, it represents the sum of all these phasors, delta E1, delta E2, delta E3, and so on and so forth. Again, in the limit when the size delta E goes to 0, and when they turn through the same angle, you are not going to get a polygon anymore. You're going to get a smooth arc, which represents part of a circle. And this circle has a radius r, which we can determine later, and the center of that circle is called point O. Okay, here is the beginning of the first phasor, here's the end of the last phasor. So this green vector is the sum of all these phasors, and that is what we're looking for. If we know this E as a function of theta, theta is the angle that is measured from the reference line, remember? Okay, if we know this angle as E as a function of theta, then we square it, we'll get a quantity which is proportional to the intensity at that in that direction, right? Okay, so the question is, how does one find the magnitude of this green vector, our resultant phasor? Okay. Now, take a good look. Okay, take a good look. This is part of a circle, and this is a radius, that is a radius. So what did that tell you? It tells you that you got a couple of 90-degree angles. This is 90 degrees, that is also 90 degrees. Because after all, the radius is always perpendicular to, the arc, right? Where they intersect. Now, here is a reference line representing the orientation of the first phasor, and here's a reference line representing the orientation of the last phasor. Okay, this is from the top of the slit, and here's from the bottom of the slit. Okay, so between the top of the slit and the back and the bottom slit, there is an overall phase difference of beta. Okay, overall phase difference of beta. And this beta in fact equals that beta. Look at the geometry here. I have a four-sided polygon, right? 90 degrees, 90 degrees. So that means this angle beta plus that angle must be 180 degrees. But these two angles added together also equals 180 degrees. So this is beta, that is also beta. Right? In order to find beta, in order to find E theta, this length, all I really have to do is find two things. One is beta, and the other is the radius r. Okay, suppose I know the radius r and I know beta. What I can do then is I can draw up a perpendicular like that. This perpendicular bisects this E theta. Then this is half a beta, right? Half a beta. And then this length would be r times sine of half a beta. Right? Let me write that down. R times sine half of beta. And if I double it, what do I get? If I double it, I get E theta, right here. E theta. So really, I have to find R and I have to find beta. Okay, now let's see how to find beta. What is beta again? Beta is the phase difference between the first beam and the last beam. Okay, go back to our diagram here. Okay, let's go back to our first diagram here. It is the phase difference between this vector and that vector, right? The first phasor and last phasor. The phase, assuming normal incidence, okay, normal incidence. So there is no initial phase difference between any of these DEs. The only reason why there is a phase difference between the first and the last phasor is because the last phase, this last DE travels an extra distance. Okay, what is that distance? A sine theta. So therefore, the phase angle difference would be k times a sine theta, right? K times a sine theta. So therefore, beta equals k a sine theta. That's beta right here. Okay, it's a function of the angle theta. That's what we're looking for. K is 2 pi over lambda, as you know. A is the width of the slit. Okay, now the tougher question is, what is r? Okay, what is the radius r? Now, I don't know what r is, but one thing I do know is that if you take a closer look at the length of this arc, okay, this part of a circle, right? And this circle actually is made of tiny, tiny DEs. All these DEs. Okay? Now, the reason why it turns is because these DEs have different phases, right? They have different phases. If they didn't have any phase difference, then all you do really just add their magnitudes up. Then you basically take that arc and you stretch it straight, right? You stretch it straight. Now, even though in reality you cannot stretch it straight because they have different phases, it actually curves around. One thing is clear, that is the length of this arc really is the sum of all the magnitudes dE, right? Isn't that true? And that sum of the magnitude has nothing to do with the angle beta. It has nothing to do with the angle beta because it just, each has a certain, each phasor has a certain magnitude dE, which is dependent upon, how intense the electric field is at that location, right? At that part of this slit. And that has nothing to do with, what angle it shoots out. Okay? So you add all these dEs up by, add all their magnitudes up, you're going to get the length of this arc. And this length of the arc, whatever it is, has nothing to do with the angle theta. It has nothing to do with the angle beta either. Okay? So it's just a constant. I don't know what it is, but I'm going to give it a name. Okay? I'm going to call it E maximum. I'm going to call it E maximum. Then isn't it true that E maximum, which is the length of this arc, over r must equal to what? E length over r. Isn't that equal to the angle beta? That is the definition of beta, right? Beta is defined as E maximum over r. That's the definition of an angle. And this tells me that I can replace r with beta over E maximum. Okay? With beta over E maximum. And the nice thing about that is that E maximum is a constant. It has nothing to do with beta, has nothing to do with alpha. Okay? Plug that in here. Plug that in, then I get E theta equals what? 2 r. R itself is E maximum over beta, so E maximum over beta. And then sine beta over 2. Okay, now let's rewrite this. What I can do is I can move that 2 downstairs. That becomes E maximum sine beta over 2 divided by beta over 2. Okay? You see, this is interesting. This is a function with an argument of beta over 2. Okay? We call that function, let's say we call beta over 2, we call it alpha. Then this is basically just sine alpha over alpha. Have you seen this function before in your math class? Well, you may have. If not, you have seen it now. This is called a sinc function. Okay? A sinc function is defined, sinc x is defined as sine x over x. That's how we define it. So basically this is just E maximum sinc beta over 2. We have successfully expressed the phasor as a function of the angle theta, okay, and which in turn is a function of beta. So basically it's just E maximum times sinc beta over 2. Now what we're really interested is the intensity. Intensity is the it has to go like amplitude squared. So as far as intensity is concerned, I have I as a function of theta should be proportional to what? E theta squared. Okay, and that's proportional to what? Sinc squared beta over 2. There is a constant E maximum squared and plus some other constants, whatever. Now, that constant in front of it, how did we determine that constant for double slit and then triple slit before? Well, we use the reference, right? We use the, we can either use the maximum intensity on the screen or we can use the intensity at the center of the screen. And oftentimes the center of the screen is where the maximum intensity is. As a matter of fact, in our case, you can see what happens, okay, at the center of the screen. At the center of the screen, what is beta equal to? Well, beta equals Ka sine theta, right? At the center of the screen, you're going, you're shooting forward directly, so theta is 0, so beta is equal to 0. When beta is equal to 0, what happens to the sinc function? What happens to the sinc function? Okay, the sinc function, as you may have already studied in your math class, looks like this. Here is x. Here is x, and here is sinc x, which is sine x over x. Now, at x equal to 0, you have sine 0 over 0. You know the limit? Sine x over x when x approaches 0? That is 1, okay? So that's 1 right here. Now, this is also an even function because both sine x and x are odd functions, so you take 1 minus divide the other, it's an even function. Without this x, okay, without this x in the denominator, the sinc, it's just a sine function, it just keeps on going, oscillating like this, right? But with this x, you have to take that sine x and multiply by 1 over x. 1 over x gets bigger and bigger and bigger as you move away. I'm sorry, x gets bigger and bigger, so 1 over x is smaller and smaller and smaller. So basically, it's a sine function with a smaller and smaller amplitude as you move away from x equal to 0. Make sense? Okay, so it's something like this. That is what the sinc function looks like. Where is the maximum value? The maximum value happens at x equal to 0, where the sinc function equals 1. Okay, where the sinc function equals 1. And of course, when x equal to 0, that means beta equal to 0, that means theta equal to 0. So, the maximum intensity on the screen occurs where? It occurs at the center of the screen. Okay, at the center of the screen. That is where theta equals 0, and if we call that maximum intensity I naught, then I can write I theta equals I naught sinc squared beta over 2. Or if I write the whole thing out, it's gonna look like this. Sine beta is Ka sine, so Ka sine theta over 2 divided by Ka sine theta over 2. This whole thing squared. Okay? This strange function describes the intensity distribution of a single slit diffraction. Okay? It's a sinc function, actually sinc squared, so we can plot how this function looks like as a function of theta or sine theta. Okay, this is sinc function itself. If you square it, you don't get negatives anymore. Everything will flip up to positive. So therefore, okay, let me plot it. Okay, let me plot it here. I as a function of theta, it's basically a sinc squared. Okay, and at x equal to 0, or theta equal to 0, you have in fact the greatest intensity. So it looks like this. Okay, now don't forget the negative has to be flipped up because you square it. So then it looks like this, it looks like this. So unlike two-slit interference pattern, which is just a cosine squared function, okay, keeps on going, never diminish. Here, it's different. You have a broad and tall central peak at theta equal to 0, okay, at theta equal to 0. And then, as you go away, you're going to have side peaks, okay? You're going to have these side peaks, you know, side peaks up, but these peaks get smaller and smaller and smaller, okay? So that is what you observe. Okay, does that make qualitative sense? Well, actually it does. Think about it. This is the screen right here. Okay, you have an opening right here, right? And then here's the pattern on the screen. So what you see is you see a bright fringe in the middle. Okay, you know that's where light is aimed at anyway, right? And then you have side fringes. So you can see some side fringes. Okay, but primarily you just see one bright fringe in the middle, and that's exactly what you expect if you have a just a beam of light passing through a narrow slit. Don't you see? It casts a bright line in the middle, bright fringe in the middle. That's what you see. The only thing that you have to take into consideration when you consider the wave nature is that there are going to be some side peaks. Okay, some side peaks. All right. Now this is called a central diffraction peak. Okay, central diffraction peak. We can study some more about this peak. In particular, we can look at where it ends, here and there. Okay, this is the first minimum. If I use a sine theta as my argument, as my variable, sine theta equals what? Well, the sinc function has the same 0 as a sine function, right? Has the same 0 as a sine function, except at x equal to 0, where it's actually a maximum. Okay, so the sinc function is 0 when the sine function is 0. The argument of the sine function is ka sine theta over 2. All right. So what we need to do is to set, if you're looking for zeros, you have to set ka over 2 sine theta. That is the argument of the sinc function. You have the argument of the sine function here. You have to set this equal to what? N pi. In order to get this sine function to be 0. This n cannot be equal to 1. Okay. It can be equal to anything but not 1, because when n equals 1, the argument is 0, you actually get a maximum, not a minimum. So n equals to plus or minus 1, plus or minus 2, and so on. We can solve for sine theta, right? What is that equal to? Well, k is 2 pi over lambda. 2 and 2 cancels. That's pi a over lambda. Pi and pi cancels, so you get sine theta. A sine theta equals n lambda. Hey, doesn't that look familiar? It says when a sine theta equals n lambda, you can get minimum. But that's exactly what we suspected. In fact, we proved that without even going through this derivation. You see here, when sine theta equals n lambda, it's dark, not bright. That will be the location of a minimum, not a maximum. We learned that in our first part of the lecture. Okay, so a sine theta equals n lambda. These are the minima, not maxima. So the very first one, what is sine theta equal to? For the very first one, n equals 1, right? N equals 1, so it's lambda over a. Okay, so the first one is lambda over a. What about the next one? Next one is 2 lambda over a. Now what about over there? That will be negative lambda over a, symmetrical. Okay, and then negative 2 lambda over a, and so on. Okay, so these are the minima. Now the maxima are somewhat more difficult to obtain. As a matter of fact, we only know for sure that central maxima occurs at theta equal to 0. Okay, that's clear. That's the highest peak. This next one is not that obvious. Okay, some say, oh, all I have to do is set the sine function to maximum. Well, look, the maximum of the sine function is not the same as the maximum of the sinc function, except the one in the middle. Okay? except the one in the middle. But roughly speaking, you can say, oh, roughly speaking, this occurs when sine theta equals plus or minus 1. Okay, roughly. But that's not exact, because don't forget you have to divide by the denominator. Okay, so it's not all that clear. As a matter of fact, if you want to try to maximize this I, what you have to do, you take derivative, right? Set the derivative equal to 0, and you find in doing so, you're not going to get a simple solution except at theta equal to 0. Rather, you're going to get something like alpha equals tangent alpha, some weird function that you can only solve numerically. But roughly speaking, they're here. And this also tells you roughly the intensity of the first side peak compared with the intensity of the center. Okay, for the first side peak, roughly speaking, this sine function goes to 1. Okay, this sine function goes to 1. But what about this Ka sine theta? This thing doesn't go to 1. Right? When sine function goes to 1. What is Ka sine theta over 2 equal to roughly? Well, if you assume, as a good approximation, that sine theta is midway between lambda over a and 2 lambda over a for the maximum. Okay, minimum is lambda over a, the next minimum is 2 lambda over a. So we say roughly sine theta roughly is equal to halfway between them. What's that? That is 3 lambda over 2a, right? 3 lambda over 2a. Okay, so that's sine theta. In other words, a sine theta equals 3 lambda over 2. Okay, so we can then calculate Ka sine theta. Ka sine theta over 2 at that point is roughly equal to 2 pi over lambda, that's K, and then a over 2, and then don't forget sine theta is 3 lambda over 2a, right? Now you cross out a's, cross out lambdas, cross out a bunch of 2's, and what do you get? You get 3 pi over 2 is roughly 3 pi over 2. Okay? Roughly 3 pi over 2. So that is what happens in the denominator. 3 pi over 2. So therefore, I at this point, the intensity at this point, let's call it I1. Okay? I1 over I0. This is I1, this is I0. Roughly equals to, okay, look. This is I0 right here. For I0, for the middle, this whole thing function goes to 1, okay? But in our case, when at this location, it's equal to I1, which is I0 times this factor, this sinc function, which is roughly equal to 1 divided by that. Okay, so it's 1 divided by what? 1 divided by 3 pi over 2. 3 pi over 2. And then you square it. Okay, that is actually pretty small. We can do a little estimation here. 1 point, it's 3 pi is about, it's about 8. Actually, it's a little bit over 9. And then you divide it by 2, you square it, you get a pretty small value. What you're getting is only about 0.045, okay? So, this first side maximum is only about 5%, a little bit less than 5% of the intensity in the middle. So you get a dominant central peak, which is wider and also brighter, much brighter. The side peaks are of decreasing intensity. Even the very first side peak only got about 5% of the brightness of the intensity in the middle. Okay, so that's a feature of diffraction. You have something concentrated in the middle. Okay. All right. Another important issue that I want to talk about is the issue of resolution. What does that mean? Well, suppose the light coming through this single slit sometimes may come in at different angles, and sometimes they may have different frequencies. Okay, in either case, we have to deal with the issue of resolution. For example, if you have two beams of light, let's say they have the same color or same frequency for simplicity. One coming in this way, one coming that way. There is an angle theta between them. Okay, as a result, each of them will cast a different set of interference of a diffraction pattern. And here's the central peak of this guy, and that green one is the central peak of the other one. Okay, now if the angle theta is really small, then you can imagine that these two peaks are going to get closer and closer together, and that they might actually be right on top of each other, in which case you cannot tell them apart anymore. So you're going to lose resolution. Okay, they appear to be the same peak. You cannot tell that there are two different peaks. So what is the minimum angle theta, such that these two peaks will appear distinctive to us? Well, one way that we can reasonably understand that is to assume that the side, okay, the edge of one peak happens to coincide with the maximum or with the center of the other peak. So we got one peak like this, okay, it's 0 is there, and we got another peak like that. Its maximum corresponds to 0, the first one. You know, if that's the case, these two peaks are barely resolvable. You can see, barely resolvable. You kind of have a peak here and a peak there, but if you get them even closer, they start to merge together. Okay, so how do we let this happen? Well, let's see here. This tells us that if you use this as a reference line here, okay, if you use this as a reference line, then this angle, which I call theta 1, would be the minimum angle between these two maxima, okay, between these two interference maxima. If the angular separation between these two maxima is less than theta 1, I won't be able to see it. I won't be able to tell them apart. What is theta 1 now? Theta 1 is really the location, the angular location of the first minimum, okay, in other words, the side of the central peak, the edge of the central peak. And I know how to calculate that, don't I? Okay, I know that sine theta 1 equals what? Actually, a sine theta 1 equals what? 1 lambda, right? That's the 1 lambda. And also we notice that the angle theta generally is pretty small. Okay, it's generally pretty small. So I can, you know, as an approximation, I can say sine theta 1 is roughly equal to theta 1 itself. So therefore, theta 1 is roughly equal to lambda over a. This is the minimum separation, roughly the minimum angular separation between two beams, so that I can barely resolve them. I can tell them apart. There are two different beams. Okay, and you can see here it depends on lambda and a. Okay, for a shorter wavelengths, I can resolve them better. If the wavelength is longer, they become more difficult to resolve. Okay, you probably have noticed things like X-ray machine. Okay, X-ray machine, as you know, has a very the X-ray that you use has a much shorter wavelengths, so they have better resolution in general than, say, visible light. Not only because they can penetrate better, but also because they can cast a sharper image because they have better resolution ability. They have shorter wavelengths. Okay, it also has to do with the width. If you widen up the gap, widen up the opening, you're gonna have better resolution. We'll see the effect of that more when we study a circular opening, which of course is how telescopes and camera lenses are shaped. They're shaped into circular opening, not narrow slits. Okay, so that is the issue of resolution.